First, I should thank the organizers for the opportunity to come to this beautiful city. Um, I guess my job is to connect theorists and experimentalists and describe some of the techniques we use for experimental characterization of um, heat and current and how they are coupled. Maybe I just have one view graph about where I'm coming from. Um, Berk Nanotechnology Center at Purdue is a place where we actually try to bring theorists and experimentalists in a diverse set of fields. So what we have is about 45 research groups and 200 graduate students that come from many applications, and it's been a very good learning experience to bring very practical people who work on food, pharmacy, and ag with some of our theorists. As I was putting the material for today's lecture together, I had some topics in mind, and I thought we should discuss what you want to hear. You know, at the end, it's 3 hours, long time. If I try to explain things you're not interested, that doesn't go very far. So some aspect of the work will be on nanoscale thermal characterization technique. How do we measure temperature at smaller scale? If you want to do any sort of energy conversion, first you need to get the temperature right. Voltage is easy, but temperature is hard. Then how do you couple or measure the coupling between heat and current? And that's the Seebeck effect and how you measure that. And then there are some special topics related to superdiffusion of heat and some of the experimental aspect of that. Can we mimic Carnot cycle with electron gas? It's a purely theoretical work, but I thought it fits here because often when we do experiment, we always think Carnot is something that we can never do. But there are some interesting things to learn. And also pushing one of the limits of temperature, some of our latest results on super resolution thermal imaging, how you can get the temperature at length scales that really in the nanoscale, and you could see some of these non-equilibrium effects. So maybe it's a good time to ask, what are the topics that you want to hear most in this list? Suggestions. If you don't say anything, I don't say anything. I go sit down and then you can enjoy the weather outside. We should use this beautiful, so there is one vote for super diffusion. Okay, well, counts enough. What else? I see. Super. They have nothing to do with each other, but anyway. Other topics. Thermal characterization in general, or any one of them in particular? All of them? Scanning thermal, optics, all? What else? Carnot cycle. This is mostly on the secondary materials. Anything else? Okay. So this is part of the standard lectures. How many students are in the audience? 7, 8, 9. You all have been the most quiet. You are the one who should benefit the most from these lectures. Maybe you should suggest something. Anything? Maybe it helps. What is your background? Physics, chemistry, materials? All physics? Okay. Maybe after listening to this morning discussion, I should add a topic about the reason I want to discuss a little bit about what I see as disconnect is um, I'm in an electrical engineering department, so I have colleagues who make chips and make devices, and I always tell them you need to hear what we are doing in the nanoscale heat transport, because at the end you want to make your transistors faster, you want to make your lasers faster, and heat is always a limiting factor. What is interesting is how little success I had to convince them to take any of our nanoscale heat transport courses. And after thinking about it quite a bit, and kind of that's one of the directions of research in my own group is going, is that if you start with the history of heat transport and electrothermal effect, they really started from very practical applications. So where we start is, maybe this is a good point to start. This is the work of Joseph Fourier in 1822. He proposed the Fourier equation for heat, which there's different ways. In the linear response, heat flow is proportional to temperature gradient, and the first order differential conductivity, differential equation that describe how temperature changes depending on the heat capacity and thermal conductivity. As you know, or you may not know, Fourier wanted to find what is the equation of motion for heat. His idea was that the equation of motion for celestial bodies have been discovered by Sir Isaac Newton, but we don't know how heat moves. And that was a time heat engines were becoming quite popular. That was beginning of Industrial Revolution. They wanted to understand how temperature changes. And in particular, Fourier wanted to calculate how temperature of the Earth changes. That's how, in this book, he derived this equation. He wanted to see if you have a hot object, how long does it take to cool that object? And in order to, and how did he come up with this equation? I guess intuition. He is actually quite remarkable when you think about it. At the time, they thought heat is a fluid, thermos, that flows from a hot object to the cold object. And they knew how fluids flow in rivers, and they knew some of the things about how equations for fluid flow it is, but they didn't know, they didn't even measure directly the heat. But with some intuition of some characteristics of the heat and some good intuition of what mathematical equations mean, he said there should be some sort of a first derivative in time and second derivative in space that are connected. And that's how we that's the equation we are using. What is interesting is, so fundamentally, you look at it, this is the temperature, the material property comes here, thermal conductivity. And that's what we write textbooks, and that's why we have studied quite a bit, I guess, in the last 200 years since Fourier. But what is interesting is what is, from our point of view, equivalent of this in nanoscale. Equivalent of this in nanoscale is I have an object or a reservoir with temperature hot. I have a reservoir with temperature cold, and I have a nano object. I kind of draw it like a molecule, but could be anything. That we call it nano object. And then we try to say, what is the thermal conductivity of this? And how this could be modified, what are some of the ballistic effects, what are some of the diffusive effects. So we take a case which is very macroscopic, and the type of boundary conditions that apply in macroscopic world, and then we kind of scale it to here. And I guess the last view graph Giulio made, this is something that we have seen a lot in top science papers. You have suspended platforms. Maybe I have one of those somewhere here as well. This is the kind of state-of-the-art way for us to mimic what happens in the large scale. You have two suspended heaters, these lines, serpentine lines. You send current, they heat up, and first of all, you put a nano object there. usually by magic. Do you know how they put nano objects there? Trial and error. Graduate students are good for that. They spend a couple of weeks, and eventually they get one nice nanowire sitting there, and this is a platform to mimic this effect. And what then we do is we send current heats up. How much heating is typically on the order of a couple of degrees with a couple of microamps. What is interesting is that a resistor that heats up, the same resistor, the resistance is a thermometer. We can measure it to measure temperature, but the current only goes through this platform, and if it's sufficiently isolated from the reservoirs outside, heat goes through this nano object. And on the other side of the nano object, so heat flows, and on the other side, we measure a tiny temperature increase. Perfect, I have temperature on one side, temperature on the other side. I can calculate the heat flow, I can calculate the thermoconductivity. And then we derive how does it change as a function of the nanowire diameters, how do you get values, so you can get the thermal conductance, and then you connect it to curves that are thermoconductivity versus temperature, and there is a lot of interesting physics. So what basically we have done is that we try to mimic in the nano world what are the real experimental conditions. But if you ask any of my colleagues who are making devices, which of your devices look like this? Never. Why would you put a tiny device completely isolated from surrounding on two sides of it? You know, never happens. So what happened is that experimentalists are interested in a different boundary condition, and that, I think, is one of the big important disconnects. So experimentalist boundary conditions are often, I have an object, could be a material, and I have a heat source. Correct? Every device that you look at it is something like this. And it's true, this heat source today is in tens of nanometers. So we need something to go beyond the conventional theory, but where is the reservoir 1? Where is the reservoir 2? Again, we try to mimic kind of the other way around. We say, let's take this and connect it to this picture that we know. And what we do is, we say I have a temperature here, hot. I put a temperature cold somewhere here, and then we calculate things. But really, boundary conditions for experiments is never two reservoirs. What is here is not a reservoir of temperature. And so what happened is that the boundary conditions, instead of mimicking these two and for us kind of putting some sort of channel between a cold and a hot, again, I'm trying to mimic, is very different, is a Q in, and then what is the temperature? That's what experimentalists are most interested to know. And what they are interested is if I make this smaller and smaller, how much it heats up. So the question is, so that I think is one of the aspects of the theory and experiment. So you say, you know, I want to work on ideal systems. If I put real atoms here, too much complexity, I cannot kind of grasp what is the fundamental scaling of when things become small. But I don't think it's impossible to simulate this case. So take the Fermi pasta Ulam kind of very simple case. Masses could be different, could be many things, but what we are interested at the end, if you could simulate it, is that put a temperature reservoir here and put a heat flux boundary conditions here. And then tell me as a function of this, and maybe if this is moving, not moving, you can put some mechanical conditions, how the scaling happens. Because the determination over length scale over which you can define a temperature, you cannot define a temperature, all of that can be defined with that. So it's not that there is no way to simplify the hard problems, but I have seen very little articles with this type of boundary conditions. So I think if you want your work to be accepted by or used by a lot of applications, try to look at the different boundary conditions. But this actually begs the question of, so we can define a temperature of a reservoir far away. We can define a heat flux here. There's no definition. But the question is here, is a single temperature correct or not? Is T, well, how to call it, a single temperature, or is non-equilibrium? And then what are the length dependence issues? So that's part of the issue that when we look at a lot of the theory papers that are done, I guess, with the community of the theories, you look at any of the experimentalists on the experimentalists, what I mean is really people who make devices, not experimentalists who try to verify the theories by mimicking what is there, like this type of thing, is playing with the boundary conditions. But I think the concept of a reservoir is important. You heard this morning, Carnot, a lot of the other discussions are two reservoirs with two definite temperature. There is no two reservoirs in a real life as far as I can see, unless you mimic it. So this become a question. How do you convert now to work? Correct? Now I have a Q that is dissipated from a laser or a transistor. I want to generate work out of it, but I don't have two reservoirs. Does the Carnot apply here? How about Curzon-Albarn? Yes. Yes. That's a very good question. So there is energy source I can describe in joules or watts and so on. So when I have a device, there is always, I know what is the energy going in, I can define it. But a question needs to be mentioned about randomness. And that's what is connected to thermodynamics. If it's a directed motion, the energy is moving all atoms the same way. Your equations of motions are different. But you could put some randomness, but how you put the randomness is important. So that's the question is, randomness as a part of a white noise, I don't know if I could define it, or I can define the temperature. These are some of the basic questions that comes here. So maybe that was a way to start the discussion a little, try to connect it. I first attended a similar meeting as this, thanks to Julia and colleagues for inviting me 4 years ago at Trieste. And it was very helpful. It actually changed the way I look at things. But it took me quite a while to go from the picture which you usually present to the picture that we can talk to our colleagues. But one of the part that a lot of people get kind of this analogy between electricity and heat. Maybe I should mention one other point about that. As many of you know, we often discover things by analogy. It's rarely people like Fourier and so on that they discover something for the first time. One of the first analogies in the field was, I told you about, oops, that was not the right view graph. I told you about this work, 1822. Just a couple of years later, Ohm came out with the Ohm's law. Correct? And it has similar kind of behavior. Electrical current density is proportional to electrical conductivity by the electric field. Actually, Ohm's credits Fourier. He got the idea from the Fourier. He was mostly interested in DC, not transient, but there is a very good connection between, everybody knows, between temperature and voltage, between heat current and electrical current, and what else? Yeah, I guess that's the two main ones. So when we look at the linear response, we took this equation, we take the equation for heat, and then we look at the cross couplings, because heat could generate electricity, electricity could generate heat. What is interesting is that Seebeck's discovery of coupling was around the same time. It's actually quite interesting. You look at history between 1820s, 1810s to 1830, 1850. A lot of the things we know today have been discovered. I guess, again, Julia mentioned this morning, Volta was just 10, 15 years before that, 1780s. There is something that I always question, and the question is the following. You look at how much of what we are using today is based on what was developed during that 50-year period. What was the world population at the time? About 1 billion. We have about 6 billion people. Just a statistical, random theory. We should have as many intelligent people now as 6 times as much as they had there. Why we don't have 6 times as much as Carnot and Fourier and so on? Any thoughts? Supposedly, education system gets better. What is part of the thing, I guess, is kind of our kind of fault as professors, is that we have made too many barriers, too many prerequisites to learn before you can do something useful. As a result, by the time you know how to do something useful, all the creativity is killed. Carnot, he was 19 or 20 when he came up with the whole thing. He did. Actually, reading Carnot's book, one of my was that 4 or 5 years ago, I actually read it. It's only 80 pages. It's not that much. The treatise. I had one for Carnot, actually. We should show his picture to be. It's my Carnot introduction. Yeah, so this is the book. 1824, again, look at the time scale. It's a book that describes actually what we think as the fundamental limit of conversion of heat to electricity today, derived by somebody who thought heat is a fluid and didn't know anything about the statistical mechanics or reversibility or Onsager and all of that. How do we teach this today? This is Carnot cycle. Obvious, isn't it? 2 isothermal, 2 adiabatic. You go through this. The maximum efficiency is -1 minus T cold minus divided by T hot. How Carnot arrived at that? By the way, again, by simplifying things, it took 200 years for us to reinterpret it. We can derive, using the laws of perfect gases, you can actually derive what is this efficiency. You can get 1 minus T hot minus T cold divided by T hot. But this equation works only in Kelvin units, correct? T should be 300 and so on. If you write it in other units, it doesn't work. And Carnot did not know Kelvin units because he lived before Kelvin. So how did he derive that? But Carnot came out with this limit. No, he does have the exact formula, yes. This is the original drawings from Carnot's book. So what is interesting is this is a theory about fundamental limits of energy conversion. What is interesting is you find a lot of experimental data in it. That was the disconnect I was talking about. His idea was, this is the, at the time it was hard to make drawings, so, it wouldn't have fancy PowerPoint animations, but something about a piston and something, and some tables for different gases, what is the elevation of temperature when they go to effect of compression. And carbonic oxide is interesting, some of these names, but anyway, nitrogen, precise measurements, 200 years ago, it's quite good. How do you derive a fundamental law? Carnot's intuition was, we make heat engines. The fundamental limit of efficiency of a heat engine should not depend on the gas that we use for that heat engine. So that's the reason he was interested in this type of tables and so on, and try to see correlations. So from the beginning, he was looking at the data and is trying to make correlations and so on. And I look hard in the book to see how this intuition came about. And actually, there was one place that his intuition was well explained. In the bodies employed to realize the motive power of heat, there should not occur any change of temperature which may not be due to a change of volume. That's his intuition. Basically, what he said is that we know all these heat engines work by motion of heat from hot object to the cold object. Let's make sure every time a heat moves, some volume changes, you do some work. That was his intuition. And that explains why we have that Carnot cycle and so on. And later on, of course, we wrote it like in this form and so on. So the whole idea is you are in contact with one reservoir, you change the volume adiabatically, you reach the temperature of the other reservoir, then you contact isothermal with the other reservoir and kind of repeat the cycle. So it's interesting, sometimes, again, when we discuss what are the limits of kind of Carnot limit is valid, is we go back, Onsaga relation should be correct, or microscopic irreversibility. Again, Carnot himself didn't know any of these. So one of the things, I don't want to do it today, it's a lecture for for Wednesday, we need to keep you here, if not you may go to the beach, is how we can use this idea to do the same thing in a semiconductor. Again, is a thought experiment, but again, is motivated with just this idea. Once you look at this, there are ways you can motivate energy conversion, which is different from what we do today. There was some discussions about how thermoelectrics, energy filtering and all of that are related. Again, on Wednesday, I will describe it. One way of looking at it, again, every representation have a limitation, remember that. There's nothing like a perfect. But one way of looking at it is that today's thermoelectric devices, based on compression and expansion of electron gas in the energy space, and that what make the work, you can mix it with the compression and expansion in real space, and then you could do a different type of work. How do you control compression and expansion of electron gas? Is typically through interfaces and energy filtering. So that's basically what happens, but we will go over that on Wednesday. Any questions so far? I'm just trying to think. I went, as I was preparing for the lecture, I was thinking this is a lecture, should be regular, this is the outline, I should go over it. And then I thought about it. I gave similar lecture, 3 lectures 4 years ago, and of course, whoever attended perfectly remembers what I said. It's a waste of time if I say it the same way. But then, let me actually show you one other thing. Everything I want to say today is available online, and you can access it. So about 3 years ago, Supriya Datta, Mark Lundstrom, and I developed this course, Thermoelectricity from Atoms to Systems. 5 weeks long. Each week is about 5 to 7 lectures of 15 minutes. Full videos synchronized by PowerPoint file. Each lecture has a quiz. At the end of each week, there is a homework. There is online simulation to run it. That is much better than whatever I could do in 3 hours here. So it's free. You don't have to pay anything. What are the topics for the lectures of week 3? Is everything that was supposed to talk today. Thermal measurements at nanoscale, scanning Seebeck, infrared thermoreflectance, thin film characterization, Harman. Okay, so in 3 years, science doesn't advance that much. Maybe I can give you in 3 minutes what has been added since then. But this is available, so it's not a good use of my time if I just repeat the same thing sequentially. And just to tell you the quality of the lectures, I wanted to show you how they look like. And this is Giulio Casati's lecture or seminar when he came to Purdue in 2012. Oops. So I guess the top of it I didn't realize. But basically what you have is that you have the view graph, you have the video, and you have synchronized. You click on each one, says the audio for that view graph. What else? You know, you can go back and forth, review it as many times as you want. And there is even a version on podcasts. You can listen on your phone. So, and I was telling you about this. There is something we professors are not doing our job because I think the creativity is not the same as it was before. Part of it is I'm supposed to give a lecture. Where the name lecture came from? Giulio, anybody remembers? That was from Italian universities in Middle Ages. What happened is that at the time, that was before Gutenberg, professor was the only person who had the book. He had to read the book, and as he was reading, students write down, and that way they have their book. They can study later. It's interesting that we are 8 centuries later, we try to do the same lectures with all this online information available. So actually, I've been thinking maybe I shouldn't lecture anymore. I have these videos. I could send this link to the organizers. You know, it's a beautiful place, but don't waste CO2 energy for me to come and give a lecture. But there are some professors here. What do you think we can do in addition to what is here? Why these personal interactions are important? They are important. We know intuitively they're important. If not, we go out of business, but yes. That's a perfect explanation, but doesn't apply here because students, they don't ask questions. Correct? If you ask, I know what you don't understand, I could tailor it, but you don't. Why don't you? That's actually one of the things. Students who don't ask questions in the lectures, you're not benefiting because you're right. If you just listen and take notes, and these days you don't even take notes, everything is available, take pictures. I learned actually quite a bit about what the lecture should be. Recently I was reading a book. I was hesitant to share that with you. It's a little old, from 1120, about study of reading. It's called Didascalion. Anybody knows about this book? It's quite old. Usually it's not part of the reading thing. But it's interesting because that was, Ivan Illich actually referred to this book. And he actually referred to this book because he said information age should learn something from a transition that happened in Middle Ages. And what we have to learn is that learning is not a transfer of information from my mouth to your ear. because that part of information through the online lectures and the textbook, everything is there. It's more than that. And more than that, because in every phrase that we use, people with experience have certain things in mind by saying that. But people who don't have that experience, they don't get it in that. So it's not an information transfer, it's a state of mind. And the only way to do it is that during that lecture, you need to be active, you need to be thinking and ask questions. And the way he was describing why vineyard of the text, in Middle Ages, this is how they wrote. No paragraph, almost no separation between words. It's very hard actually to read it. I cannot read Latin, but even if I could, it's not easy to read. They actually made it not easy to read. Why? Because they said by not being easy to read, the students make an effort. By making an effort, they learn things better. And I think now with all the information we have, everything on the podcast and so on, the effort goes to zero, and this transfer of information doesn't go as well. I guess enough philosophy for today. So I discuss about, so what should be the order we discuss about this? Thermal characterization, Carnot. I told you a little bit about Carnot. Rest of it is Wednesday. Today I want to talk to you about thermal characterization technique, and tomorrow about super diffusion, super resolution. Anybody wants to change the order? Is that good? So let's go to the thermal characterization technique. So what is the thermal characterization technique? You have an object, you need to measure its temperature, for example. How do we measure temperature? A physical property that changes with temperature. This is a thermometer, the volume changes with temperature. You calibrate it, this is how that physical property is related to temperature. One of the first, so how do you measure? You need to connect it to your object with something that has a low thermal resistance. In practice, there is always a finite thermal resistance. The ideal contact never exists. And for nano, we need to worry about that even more. And then we need to make sure we are not connected to other objects, because if not, we measure the temperature of not only this, but we measure the temperature of the others. And the view graph is easy. Julia already mentioned what is the key challenge. Again, analogy with electronics works quite well. You say it's the same thing. I have a voltmeter. I use the old voltmeters, like something that moves around when you measure the voltage, correct? I have a nanoscale transistor. I try to be more exact because I want to show what is a transistor. There is a source, there is a drain, and I connect one side of it here, I connect the other side here, and with the gate, I control what is going between, but I measure the resistance or equivalent resistances of this object using this. The electrical conductivity of the wires are many order of magnitude more than this channel. And the electrical conductivity channel is many order of magnitude more than all the surrounding. Because I have 20, 30 orders of magnitude in electrical conductivity values to play with. This does not work for heat. That's the biggest challenge. Analogy is there, just order of magnitudes, they don't play as well. So how do you do heat conduction measurement? This is the type of measurement I told you is not excite as much the experimentalists, but still. How we do today, we put a reservoir, heat source, we mimic them well. Again, it's not a real word, but we measure a heat flux temperature difference, we connect it. What is interesting is the best way to describe this object or heat transport, which comes from analogy with electrical transport, is Landauer formalism. Julie, are you going to talk about Landauer tomorrow or something? Perfect. So I should wait for that. But what it is that this is a very nice formalism from an electrical transport to tell you in these objects, when I go from length scales of tens of micron, when this is a real resistor, Ohm's law apply, to today's length scale, tens of nanometer, where Ohm law does not apply, perfectly explains. Perfectly explains because I can have a reservoir of a high voltage. I mean, I should have put some sort of a voltmeter applied to here and send the current. But anyway, I can define a voltage at the source. I can define a voltage at the drain without a problem. And because wires are reservoirs, in this case, we can mimic it, but really in reality, we cannot do with the heat source. I mentioned the example, which was somewhere, I guess, up there. What we need from theories is equivalent of Landauer for those type of boundary conditions. For heat is really necessary if you want to connect it. So quickly, a table with all the ways to measure temperature. Again, the numbers, you can look at the paper, you can look at the view graphs from the online course, everything is there. But what is important is that resolution in space, resolution in temperature, resolution in time, is it scanning or imaging technique, is just how fast you can get it and some of the limitations. Most of the work that is related to nanoscale heat transport is done with scanning thermal microscopy, is one example, and one version of this is suspended platform. Near field optics can go to very low spatial resolution, 50 nanometers claim, but as far as I know, nobody uses that in any practical experiment. Why? It's not that it's not impossible, it's this is so sensitive to parasitics that often you need a PhD student and 6 months to get one good data point. Perfect, you can write a paper for Nature and Science, but the next paper depends on other students getting trained for 2 years. It's not very student-independent effect. So this is, in practice, I don't know, I mean, you can still write. I was actually comparing to 4 years ago, some of the things that has been done. There have been some advances in scanning tunneling microscopy. Here, I have not seen any new articles, and I will describe it on Wednesday about some of the near-field radiation work. Raman measures temperature using an optical effect, which is Raman. I will describe it briefly. Optical interferometry really measures a change in distance. But because objects expand as they heat up, this is a good way to measure distance. This is amazing part of the optical interferometry. The spatial, again, maybe theories they don't appreciate what interference effect could do. Do you know how sensitive is the interferometers to the motion of the samples? What is the smallest distance we can measure practically in the lab? Again, not in state-of-the-art things that is, at certain labs and is not as reproducible. Something that you can build in 1 or 2 years in your lab and works. What is our sensitivity to expansion? Physical numbers. Angstroms, 10 minus 10 meters. Whoever higher bids? That's higher, 10 to the minus 9 meters. That's why you need in your community some more experimentalists. We can measure motion of surfaces. So I have a surface. Let me explain what I'm saying. I have an interference pattern with a light and another mirror. By measuring the fringes of this interference, I can measure a change in surface, which is 10 minus 15 meter. Diameter of the nucleus, not even the atom. You can do it. No, gravity waves, they go to 10 minus 21. Small detail. 10 minus 15, you can do it very quickly. is any you have just to have a good interferometer. Why is it? What is interference? You have thousands of wave numbers. You just move a little, is multiplied by this wave number effect. That's all it is. But that's a reason they can measure 100 microkelvin temperature, but you need to relate that to a physical expansion. Depends what is the volume. So it's not, if you know a lot about your sample, is useful. If not, you cannot connect it to temperature. Thermoreflectance, I will describe heavily. Liquid crystal, IR, I should not go over it. Correct? Anybody wants to hear about any of the other ones? Let me just go to smallest, and the simplest one is thermocouple. By the way, thermocouple is what Seebeck discovered. A voltage that is created due to temperature difference. This is the smallest thermocouple you can buy. It's about 50 micron bead diameter. The diameter of the bead, the wires are 25 micron. It's very fine. So students need to handle it, but before they have too much coffee and too much agitation, doesn't work. But you put a piece of this on a sample, a piece of this as a reference. Reference for thermocouples is very important. You can measure temperature quite accurately. This is one of our early work. Actually, it's a tiny refrigerator, 4-degree cooling. You can measure it beautifully. But thermocouple measurements are notorious for you need to be very careful about how you contact your object. You always measure a temperature, but that's the temperature of the tip of your thermocouple. That's not necessarily temperature of your object. And as I said, in a real world, nothing is perfect. So in a real world, what you have, now we have to use the technology of erasers. So what you have is, you have an object that you want to measure its temperature. You put the thermocouple, which is a junction between two materials, material A, material B. Typically, you melt them here to create the junction. This diameter can be as small as 25 to 50 microns. But the contact here, dry contact is not good. Often what we do is that we touch a little thermocouple, a little fluid, so that it has a good connection. So here is thermal paste. And what you need to learn is how to apply. If you put too much, doesn't work. If you put too little, doesn't work. But this is the kind of thing is reproducible. You can measure temperature typically with 0.01 degrees C. I don't know what I said. On that order can be done quite well. At room temperature is easy. What I mean is that if everywhere is 300 Kelvin, and here is different, here is 298 Kelvin or 310 Kelvin at this location. This is easy. Why? Because the rest of the medial, all equithermal, you don't have parasitic Seebeck voltages. That then you measure a voltage. But if ambient is 300, but you are trying to measure something at 1 Kelvin, or you want to measure at 500 Kelvin, then what happens is that you can have a fraction of the heat that goes through the wires. And whenever heat goes through a thermal resistance, you have a temperature drop across the thermal resistance, you get misreadings. So a couple of minor details. How do you miniature this? And this is a work from almost 20 years ago, Majumdar's group. At the tip of an atomic force microscope, which is shown here, 10 micron scale, at this tip, they make a junction between platinum and chrome. And you see the scale, very tiny thermocouple. And they touch the surface. It comes to the surface. And here is a probe. You want to measure its temperature. Here is a sample. Early on, people were naive, like any time in the field. You always neglect and non-idealities. They say the tip could be 1050 nanometer. My resolution is 1050 nanometer. Later on, people realized that's not the case because at room temperature, most surfaces, they have a tiny layer of liquid, right, humidity on top. And the heat transfer through this water expands the region you wish to measure the temperature. You have some near-field radiation effects, conduction air effects. In reality, temperature resolution is 100 of nanometer, but which is quite reasonable. This works quite well if the surface has some roughness, but does not have any general kind of non-idealities. This is some of the early work from Majumdar's group. This is a single var carbon nanotube. They send current through it, and here is thermal images at different voltages. Beautiful. You can see at high voltages, the whole thing heats up. At small voltages, you see heating at the contact. You can separate the contact from the carbon nanotube joule. Works perfectly. You write papers, in nice journals. You put in a practical sample. This is the kind of thermal images you get. You have never seen this in any journal because we did not publish it. You cannot publish something like this. This is a refrigerator that is cooling 2.5 degrees below ambient. You can kind of see it, but you see all of this artifact. Temperature cannot jump that quickly, correct? You just know. Why it is that you're coupling, as you scan the surface, the roughness at the surface is not always the same. How do you ensure that? So it's practically impossible to do thermal images. Single point measurement, perfect, you can do 1 point. Imaging, if it's perfectly flat like carbon nanotube or graphene, perfect. Anything else, good luck, because you can never separate, correct? If there is a different roughness, the temperature at different locations could be different. And so there are two effects the thermal image, the morphology and temperature, and it's very hard to separate it. So how is Raman working? Is another physical property that changes with light. Every bond has a resonance, that's quantum mechanics. But at room temperature, there are vibration states because atoms are not just sitting there. So in addition to the bonds energy quantization that happens with the atoms and molecules, you have a finer variations, vibration energy states that are different. The energy differences is very little comparing to the fundamental energy difference between the two states, but you can resolve it with good spectrometers. And typically, you can have energy of the incident light coming and light that is emitted a little lower energy. That's called Stokes process. And this is, I guess, this one. Or you excite from excited states, but you go to the ground state. The energy is higher, and this is the anti-Stokes, and this is this peak. So the position difference, Stokes and anti-Stokes, is symmetric because it's related to the energy differences in the ground state. But the amplitude of the red one is more than the blue one. Why? Why there is more scattering in Stokes than anti-Stokes? Sorry? Yes, so basically this one goes from ground state to this state. So the population in this state is more than this one by the Boltzmann factor. So this is your thermometer, Boltzmann factor. The ratio between amplitudes, oh, I didn't put the ratio. I forgot that view graph. But anyway, you have it in the online version, cleaned version. But anyway, the ratio of these two, you can connect it to a temperature. That's a thermometer. What is, in practice, things that could affect these measurements? If there is a absorption in the medium that depends on the color, then the ratio could also depend on the absorption of light. You need to calibrate for that. But it's possible, and people have done it. Raman measurements give temperature resolution of about on the order of a micron. It's used quite a bit for 2D material because you can get a good Raman shifts and Raman amplitudes. By the way, the actual amount of the shift is also depends on the temperature, and that has to do with the bonds, how they change with temperature. So you can use both of them as a thermometer, but temperature sensitivity is a couple of degrees. You cannot do very fine. And So I think this is basically what I had for today. So I guess for tomorrow I will go over some of the other um, super resolution and thermoreflectance, and then on Wednesday discuss some of the energy conversions. For those of you who want to benefit more from the lectures, go on the online course and see if there's anything you like to hear more. But now that I'm here, it's better to answer questions and so on. Okay, thanks for your attention. Questions? They need some stimulants. Oh, you have a question? Yes. Yes. Yeah, there are some of these effects that have been done measurement, but actually you mentioned a very good point that I kind of put it under the rug. This type of 1D simulation, the boundary conditions, um, inherently with the boundary condition, I said it's not very helpful from a theorist point of view because you make the chain longer and longer. You have a reservoir section, but your thermal resistance keep increasing. So somehow you need to normalize to the closest point where you can define a temperature and then look at the scaling. If not, you get a big trend, and on top of a big trend, small variations. I don't know if I answered you, but people have done length dependence thermal conductivity, and they see this type of fractional length dependence. Yes, very new, I guess. You are going to talk about it? A little bit, okay. 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 Any other questions? Okay, enjoy.